have several questions from Slack. Is Jonathan here? So he asks all those great questions, but he's not in the call. Yeah, maybe I'll read the question from him and just to so Nitish can answer here also. So he asked from the picture in slide 13, it seems like SPOO and SPOT have the same average request distance. Maybe in both cases, this can be even calculated explicitly in closed form. But shouldn't SPOT visibly behave better as it has one more option?
Okay, so actually, because of the scale of the plots, it might seem so, but in practice, we did get SPOO performing better with respect to request distance. But yeah, there is not such a visible difference in terms of request distance. But one reason might actually similar behavior we also find for POT and PO. I guess this was fine with that, but with respect to spatial PO and POT, I think with uniform placement of the servers, it's the difference is not that large for PO because maybe the probability that you get a nearest server versus the probability that you get two nearest server within a particular region of or a circle of radius r around you for uniform placement might be similar. I'm not entirely sure, but at least I think this is because of we are placing the servers uniformly at random. Because of that, this behavior might be evident. Maybe for yeah.
Sorry. Did you see SPOO is like better in terms of distance with respect to SPOT?
Yeah. We did see, but it's not that much. Like he pointed out, it's not visibly evident. So there's no such drastic difference between them. But if I reduce the axis of the y-axis plots and then show, and then you guys will be able to see.
I see. Okay, yeah, I think he asked shouldn't SPOT be better? So, but yeah, you can address his questions in more detail in Slack. Okay. Yeah. So next two questions come from Isaac. So Isaac,
just to point that out, I expect SPO to be better. Because you just directly go to the nearest server. So that's the optimal policy with respect to request distance.
Yeah, I guess SPOT also takes into account of the load, like not only based on the distance, right? Okay. So Isaac?
Right. So what I was wondering is, it seems like your simulations were at relatively low load, and at high load, like approaching capacity, a policy like SPOO, SPOT, these all should be throughput optimal, because just by luck, there'll be some servers that get overloaded by having too many nearby users. Did you look at it as load increases?
So yeah, for SPOT, what we observed is that we only got the lower bound on the load. We haven't exactly calculated what would be the maximum load behavior. So at least now we do not have, as of now, we do not have the plots corresponding to that. But you are correct. But that may not be true for the case when you have servers placed uniformly at random. Maybe I expect that behavior for the case when you have clustered servers. In that case, you might find that the one particular server is overloaded because it has many nearby servers. But for uniform placement, I do not expect that behavior.
but I guess just by chance, one would expect there to be some, clusters forming just by luck, even if they're fairly mild clustering, because you're never moving
Probability
them.
of that may be 0 when you scale n to infinite. Maybe.
Oh, okay. So for any constant load, as number of servers goes to infinity, you might still have stability, potentially.
Yeah.
Okay.
But we haven't looked into that.
Of course. Thanks.
Yeah, just a follow-up question. So in the simulations, so did you consider like a fixed number of arrivals, or like do the arrivals happen dynamically?
So there's no dynamicity here. We have equal number of servers. You can map it to a balls and bins problem where you have n balls and n bins. You sequentially allocate balls to bins, so there is no dynamicity here.
Okay, so there's no departures in the model, right? Okay, I see. Okay, so next question comes from Ziv. Ziv, please go ahead.
Hi. So I had a question about d power of 2, and which is basically how sensitive is the performance of d power of 2 to the specific probability weight you use to go from distance to probability. So for example,
this is a nice question. So we did try different exponents. So we did try 1 over d, 1 over d squared, and 1 over d cube. And with that, what we observed is this d is equal to 2 has this sweet spot where we achieve maximum performance. It may be with respect to the dimensionality of the Euclidean plane. So because we are considering...
That was my next question, yes.
So because we are considering 2D plane, so we are getting these results. We are yet to try it for a 1D line and see if d is equal to 1 gives you better performance than d is equal to 2. So yeah, that is one of our future works.
Okay, thanks.
Yeah, so did you actually make use of the fact that this is a 2D space? What will happen like if you have a 3D space?
Oh, we haven't explored that yet. So
Okay.
that might be a conjecture that you set this exponent 1 over d cube if you are going for 3D space. But that's something that we haven't explored yet.
I see.
So actually, sorry, to keep going on the topic of the space. So you could approximate the Earth as not as a, I guess no one really builds data centers on the poles, so as a band, which is basically the unit square where the left and right edges are the same, are glued together. Have you tried any simulations on stranger spaces like that? And I sort of imagine everything should still work, but that might be an important consideration.
That's a nice suggestion. We haven't explored that aspect, but we are certainly planning to expand it for the case when we have a graph and the servers are interconnected with like in a graph, and all those graph structure we are planning to consider. But the thing that you said we haven't explored yet. But that's a nice suggestion.
Okay, so other questions?
May I have the very last one? I don't know. So I understand that you will consider different graph topologies in the future work. But for example, if you assume that people are dense in some area, and if you put more servers in these areas, do you think you can extend the results you achieve for uniform distribution?
So are you trying to say, like, for the case when there are not equal, like here we have considered the case when you have equal number of servers and users. Are you trying to suggest for the case when we have an higher number of servers compared to users? Or
what I would mean is that, imagine you are in a city, right? The city center attract more people, right? So I would expect that I would have more people in the city center, and I would allocate more servers in the city center, right? So if you match, you balance, you provision the resources where the user will be located. So that then you think that you can extend the uniform, the results you achieve with a uniform distribution of users and servers.
I don't expect that. So when you do not have uniform users and servers, particularly servers uniformly distributed, I do not expect these results to be applicable there.
Okay.
But because at least with respect to maximum load behavior part, we do not expect that. We might not get better performance with respect to maximum load part, but definitely with respect to the request distance part, that will be reduced. So if you adopt a policy such as DPOT, then your request distance behavior will be better than POT or other policies available. But with respect to load part, we are not sure. We may not get similar load benefits as that of POT in that case.
Okay, thank you.
Yeah, welcome.
Okay, I think with that, we will conclude this session. And thank you. I'd like to thank all the speakers for the great talks, and thank you everyone for being here. And let's thank Danilo for doing all the organization work. So do you have? So do you have anything you want to announce, Danilo, before we end today's
no,
session?
actually, today we don't have. Tomorrow we will run the full session of the conference. We don't have any additional event. While on Thursday we'll have the keynote by Professor Amy Ward, and actually Amber, she's online, and she's is a joint work with Amber. So I would invite you to rejoin the keynote. I understand that it is very very late according to where you are located, but I think it is worth waking up early. And so hope to see you online in the next days. And actually, this is the very first time we meet online. So Waynar, really thanks a lot for the great work you also did as a publicity chair. I thank all the publicity chair during the introduction, but since I have the opportunity, you also helped me a lot. So really thank you. And thanks to all also for staying up to this time, to the very end of the session today. So see you the next days then.
Yeah, thank you, Danilo. It's my pleasure. Yeah, thank you.
Okay, so see you tomorrow. Ciao, bye-bye.
Bye, everyone.